Hello, this is Kathleen Hornberger. I'm a PhD candidate at the Biopreservation Core Resource at the University of Minnesota. Today, I'll be talking to you about the optimization of DMSO-free preservation methods for NK and NKT cell subsets of PBMCs. Cell therapies typically have a short shelf life, but these cells must survive a complex supply chain where they may travel from a collection site to a manufacturing site and finally to a clinical site. Cryopreservation is often necessary to keep cells alive throughout this process. Currently, cells are preserved in solutions containing dimethyl sulfoxide, or DMSO, which is cytotoxic and results in increased cell loss the longer the cells are exposed. In this study, we explore the effects of various DMSO-free cryoprotectants, all made up of the same three molecules, on both NK and NKT cells. Our goal is to develop DMSO-free preservation products that make cell therapy preservation easier and more effective by alleviating the time constraints due to cell exposure to DMSO and improving cell survival and function. PBMCs from 4 healthy donors were frozen in combinations of osmolytes, inspired by how trees survive freezing in Minnesota winters, including trehalose, glycerol, and isoleucine. Cells were frozen in a controlled rate freezer at -1 degree C per minute. A differential evolution of multiple objectives, or DEMO algorithm, was used to optimize the concentration of each osmolyte for maximal survival of both NK and NKT cells. 4 generations of 8 solutions each were tested, for a total of 32 solutions. Post-thaw recovery of NK and NKT cells was measured using flow cytometry. The optimal NK solution increased for each generation, with the best solution resulting in 93% NK cell recovery, as shown in Figure 1. We found that the NK and NKT cell populations did not optimize together. This same solution corresponds to only 55% NKT cell recovery. Figure 2 shows the optimization of the NKT solution. The best NKT solution, resulting in 91% recovery, corresponded to only 81% NK cell recovery. Comparing the levels of each component in the 2 optimal solutions, listed in Table 1, further shows that the different cell types have different cryopreservation needs. The optimal NK cell solution favored the highest concentration of isoleucine tested, while the NKT solution favored the lowest amount. The 2 optimal solutions also had differing amounts of both sucrose and glycerol. Our findings show that preservation is not one size fits all. Care must be taken when preserving multiple cell populations to select preservation strategies that maximize recovery of each cell type. The comparison of NK and NKT cell recovery suggests that there are different mechanisms of damage for each cell type during cryopreservation. Additional molecules may need to be considered in order to find a solution that protects both NK and NKT cells simultaneously. Looking forward, we are in the process of developing a DMSO-free cryopreservation solution designed specifically for natural killer cells. We recently participated in the National Science Foundation Innovation Core program, where we interviewed 150 stakeholders in the cell therapy space about pain points surrounding their current cryopreservation practices. Based on our findings, we're commercializing our DMSO-free preservation solutions optimized for different cell types through Blue Cube Bio, a company spinning off from the University of Minnesota. We currently offer products for preserving mesenchymal stem cells and pluripotent stem cells and are moving towards commercialization of preservation products for T cells and NK cells. Please feel free to check us out at bluecubebio.com. Thanks for listening.